In our previous part, we have converted our mechanical differential equation into electrical one over here, and after that we are having these four equations which are over here. So this is our first equation, which has been called as equation 1, this is our equation 2, and this one is our equation 3, and this one is our equation 4. So just looking at this analogous chart, we have converted our mechanical differential equation into our electrical one over here, and we no longer do require these mechanical equations over here. So I can do erase these mechanical equations over here, as we have already interchanged or converted that mechanical equation into an electrical one over here just by looking at this analogous chart over here. So in our next part, we do require to transform or do require to further convert our given electrical equations over here. And how to do that, let us go for the consideration. For that conversion, we should utilize our analogous chart over here. So I'm just going to take this analogous chart over here, which is the number 5, which is our angular displacement. So for that one, we can say that the theta t, which is quite naturally our angular displacement, that is equal with our charge, which is our qt. Now, according to the definition for our analogous concept, we can say that the theta t is analogous or equivalent or equal with our qt. Now, if you do take the derivative on both sides with respect to our time, we are having this one, which is our d theta t by dt, which is quite naturally our dqt by dt. And according to the definition for our current, we do know that the rate of change of charge with respect to time, that actually give us the considered part for our consideration, which is quite naturally dqt by dt, which is quite naturally the definition for our current, which is our it. So it is nothing but the dqt by dt. Now, with the help of this expression, we are having that it is equal to our dqt by dt. Now, if you do cross multiply on both sides, we have got it dt, which is our dqt. Now, if you do take the integration on both sides, we have got this one is our dqt, and this one is our integration of our it dt. And quite naturally, the integration of our dqt, that actually gives us qt, that is nothing but our integration of our it dt. So we are having these two important relations over here. So I just do require to note down over here. So the first relation is our dqt by dt, that is our it. So this is our first relation. The second relation will be our qt, that is quite naturally our integration of our it dt. So these two relations are quite vital for a considered point for our consideration. So what is the take for our present consideration? We have considered our number 5, or number 5 considered for our analogous chart over here, and we have considered that over here, which is theta t is equal to qt. Now, if you do consider, or if you do take the derivative on both sides with respect to our dt, we are having d theta t by dt, which is dqt by dt, and dqt by dt, according to the definition for a considered part for a consideration, the definition for our current is our rate of change of charge with respect to time, that actually give us the considered part for expression, which is it. Now, we have got that the dqt by dt, that is our it. So we have noted down over here. So in our next part, according to a definition for a considered part, we are having it is equal to dqt by dt, and we just cross multiply that part for a consideration, which is it dt is equal to dqt. Now, if you have taken integration on both sides, we are having qt is equal to integration of our it dt. So we have got these two important relations over here. So let us do replace these two relations on that given four equations over here. So the first important relation is quite naturally dqt by dt, which is our it, and qt is integration of our it dt. So we are having these two crucial relations over here, and let us to replace that in our given four equations over here, and let us see what is going to be the change form over here. So after we have replaced that given relation over here, so the first relation will become et is quite naturally our L1, this one is our di1t by dt, because we do know that dqt by dt is quite naturally our it plus our 1 by c1, and inside our bracket the qt is quite naturally our integration of it dt. So this one will be our i1t dt minus, and this one will be our i2t dt. So this one is our first equation over here. So this is going to be our equation 1. So in our next part for our equation, if you do replace these two relations over here, so what is going to be the relation? The relation will be L2, this one will be our di2t dt plus 1 by c2, and inside our bracket we do have our integration of our i2t dt minus integration of our i3t dt for this one. Okay. Similarly, plus our 1 by c1, inside our bracket we do have q2t. q2t means our integration of our i2t dt minus our integration of our i1t dt, that will be equal to 0. So this is going to be our equation 2. So we have converted our two given equations over here. So let us move on towards our next equation over here. As we have already converted these two equations over here, so we can erase these two equations over here. So the equation 1 and 2 will be eliminated just by simply replacing these two given crucial relations over here. So moving on towards our next relation, which is quite naturally our equation 3. So let us do replace that on that one, and let us see what is going to be the change from over here. So for that next part for equation, the next equation will be our L3, this one will be our di3t divided by dt plus our R3, this one will be our I3t plus our 1 by C2, this one will be quite naturally the same one over here, which is integration of our I3t dt minus of our integration of our I2t dt, okay, plus 1 by C3, and inside our bracket we do have our q3t means our integration of our I3t dt minus this one will be our integration of our I4t dt. This will be equal to 0. So this will be our equation 3. Okay? Yes, this one is the correct one over here. So let us do the same for our fourth equation over here, or fourth or the last equation, that is quite naturally the most important one over here. So how do you replace that these two relation at the fourth equation over here? So let us just go for that considered part over here. So for that next equation we have got, this one will be our L4, this one will be our di4t by dt for this one, plus R4, this one will be our I4t, plus the last one will be our 1 by C3, and inside our bracket we have having I4t minus dt. This one will be our I3t dt. That will be our equal to 0. So this is our fourth electrical equation over here. So ultimately we are having these four different equations over there, and in our next level or in our next part for consideration, we do require to form the torque voltage analogy over here, and quite specifically we do require to form the electrical equations just by looking at these four different equations over here. So what is going to be the most important part in this present part for consideration? We are having our four electrical equations over here, and we have replaced or we have modified our previous electrical equations over here just by utilizing our given relation over here. So the first relation is, I am just going to refresh your mind once again, or I am just going to tell you over here that that first relation is our dqt by dt, that is our it, and qt is our integration over it dt. And how do I get those expressions over there? I have already told you, or I have already given you the exact way to form this relation over here. So I have just included, or I have just utilized these two relations to modify our further four electrical equations over here. So in our next stage, I am just going to form the electrical circuit, and that will be the last part for our solution for our torque voltage analogy problem 4. So just wait for the next part. So at this last stage, we need to form the circuit diagram just by looking at these four crucial equations over here. So let us just go for that one over here. So just by looking at this first equation, we are having our voltage source of ET that has been included over here. So I am just going to include the ET over here. So this is our ET that is been included over here. And with that one, the inductor is being placed over here. So I am just going to include the inductor L1 that is being included over here. And the capacitor is placed in between our current I1 and I2 over here. So I am just going to include the capacitor C1 over here. So the C1 is being included over here. And in this loop, the current is quite naturally our I1T. So this is our I1T. So if we just go for that next loop, we can see that or if we just look at this next equation, which is our equation 2. So in this loop, the L2 is being present over here, L2, and the C2 is already been included over here. So we are going to include the C2 over here. And as you can see that the C1 is already been placed in between our current I1 and I2 over here. So in this loop, the current will be our I2T. So this is our current I2T over here. So moving on towards our next part, we can see that the L3 is being considered over here. So this is our L3 that is being placed over here. And of course the R3 is also being considered over here. So the resistance R3 is being included over here. And we are having the C2 is already being considered over here. So we no longer require to repeat that one over here. And quite naturally the C3 capacitor is being considered over here. So this is our C3 that is being placed over here. So in this given loop, the current will be our I3T. So moving on towards our last equation, which is this one. So for that one, we should include the inductance over here. So the inductance of our L4 that is been included over here, and the resistance of R4 that is being considered over here. And in this given loop, the most recognized part for our current is our I4T over here. Okay, so this is the final diagram for our torque, voltage analogy. Okay, now how do you get to that considered part over here? So if you do say that this is our loop 1, this is our loop 2, this is our loop 3, and this is our loop 4. Now if you do apply the KVL in our loop 1, we are having this equation 1 over here. Now let us just take that over here. So the voltage itself, which is ET, the voltage drop across our inductor L1, that will be our L1 di1 t by dt. The voltage drop across our capacitor will be this one. And why do I consider that the difference of our resultant current will be this one? Because the capacitor is being placed in between our two current elements of I1t and I2t over here. So the first equation is settled over there. In our next equation, we are having the voltage drop across our inductor will be L2, and so we have included the L2 over here. And the C2 capacitor is being placed in between our current I2 and I3t over here. So in between our I2t and I23, the C2 capacitor has been considered over here. And we have already included the C1 capacitor that has been placed, or that has been considered in between our two current elements of I1t and I2t over here. So that is already been included over here. So this one is being properly considered over here. Now if you do apply the KVL in this closed loop, we are having this equation 2 over here. Similarly, for our third equation, we are having this equation over here. And once again, we are having our inductance of L3 that is being placed over here. So L3 is being considered over here. The voltage drop across our resistor will be this one. So quite naturally, the R3 is being considered over here. And the C2 capacitor that has been placed in between our two current elements of our I2t and I3t over here. So the C2 capacitor has already been drawn by me at the previous equation over here. And for that last part of our equation, we are having the capacitor 1 by C3 over here. So the C3 that is been included over here, and the resultant current across our capacitor C3 will be our I3t minus our I4t. Because of that, in between our I3t and I4t, the capacitor C4 is being placed over there. Now, once again, if you do apply the KVL in our loop 3, we are having this third equation over here. So at the last stage, or for the last loop, we are having our loop 4 over here. So once again, if you do apply the KVL in our loop 4, we are having this equation. So let us do check over here. So the voltage drop across our inductor L4 will be this one, the voltage drop across our resistor R4 will be this one, and the voltage drop across our capacitor will be our this one. And what seems to be the resultant current in between our capacitor C3, the resultant current will be our I4t minus our I3t over here. So that will be equal to 0. So these are our four equation, or four differential electrical equation that we are having over here. And from that one, just by applying our KVL expression, we have checked that that this is the final torque voltage analogy over here. So this is the opposite form of our considered part over here. In our circuit theory analogy, we do know that that from that given circuit, we do require to form the much needed electrical equations over there just by applying the KVL, KCL, what is required for that circuit diagram over there. But in this torque voltage analogy, we have totally gone opposite direction over here. So just by looking at these four crucial or important electrical equations over here, we do require to form our much needed torque voltage analogy over here. So this is the torque voltage analogy additional problem 4 over here. So you can see that we have totally given you the total picture over here. So what are you waiting for? Please do subscribe our channel, hit the bell icon for more updates, and stay tuned to the classes. And you can do feel that no other YouTube channel would like to give you this detailed analysis over here. But I am just assuring you that we are just going to give you the total picture over here. So that is the specialty for our engineering classes. What are you waiting for? Please do subscribe our channel, hit the bell icon for more updates, and stay tuned to the classes. And I can challenge you that no other YouTube channel will like to give you this type of detailed analysis over here. So stay tuned to the classes, do follow our videos. That's it. Thank you and goodbye.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.